first speaker, Matt. Matt currently straddles two positions. He's at WHOI here for his research, but he's also based in Nova Scotia in Canada with RBR. Matt's early career work sort of focused more on sort of continental shelves, looking at the interplay of sort of topography, wind, currents, and subsequently sort of moved into looking at the influence of fine-scale physics on carbon export. Over to you, Matt.
Thank you, Philip. Hi everyone. So yeah, I'm part of the. I don't even really know how I'm going to articulate this, but I'm going to try. I'm part of that missing flux working group that was on one of the 4 or 5 now, I think. I know it's that classic case when you have an area of expertise, and then one day you kind of see a problem, and you're like, oh, actually, it's not really my wheelhouse, but I have all the tools to answer that, so maybe I'll look into it for a couple of years. And then like a couple of years later, Adrian reached out to you and be like, oh, actually, you should lead that working group about that topic that you're really not familiar on. So this is the result of that and me saying yes to that. I'm the one standing. I did very, very little work except putting the slides together. These all smiling people actually did most of the heavy lifting, and it's very, very, very much still work in progress. So this is where we are for now. And I think the objective of doing this today was really to also, bounce back on the community and things that you're aware of and that I'm not. Again, it's not my field of expertise. I'm very much standing on the fringe of that. The imposter syndrome is very, very present right now. So if you know of things that we should know about, if you're aware of work that you should point out, this is the whole point. This is to have this conversation. So please mention it. So I think it has a theme now, but we all pulled out that diagram just because Adrian used it on the number 1. And I look into this, and everyone points at the complexity of it. I actually don't know what you're talking about. The physical problem is super simple. It's a single arrow, double pointed, just in case, cover all the bases. And then that's it. The work is done. And then, as Adrian said, it's just the first result on Google image. So I figured maybe if I go to the second result, it'll be great. Same results. Couple of arrows, couple of words, and then that's taken care of, often in the corner. Just don't see it too much. And so I think this is something that as I'm part of this community and I listen to conversation more and more, the mixing pump, everybody knows about it, everybody's there. Some people know that it might be important. But I do think there's a push more and more, and I've noticed that as I reviewed the literature, is every more recent publication actually focuses a little bit more on that part of the pump and its contribution. And that has different reasons. Maybe awareness is one of them, but also technological tool, when you're with model resolutions, shrinking down, aligning more physical processes that we didn't necessarily were able to capture before. And I think Amela will talk a little bit about that in her talk. So looking at that review paper by some of the names that you recognize here, most of those are in the room actually. It's really broken down in like 3 different processes. So the large-scale subduction pump, which engulfs all of those terms that are quite general, and so I'll talk a little bit about that. And then the mixed layer pump, which is a lot more defined, and I'll also think, I'll talk about why I think this is the case. And then the last one being the AD subduction pump, which is really everything that has to do with mesoscale and sub-mesoscale physical processes. That's kind of moving things in the upper part of the ocean, and I think is the reason why I'm standing here today. Okay, so I'll tackle them separately because someone said yesterday, I think it was you, Svenja, that said, what's the first step you take? You divide and conquer, right? So we broke it down in 3 different themes and kind of went our separate ways, and then everyone contributed to different themes, and then we tried to pull it all back together, which proved to be really difficult. But so the first component is that what's the large-scale subduction pump, and so this is all based on my kind of overview of the literature of what I'm aware of in the literature, and turns out there is almost no literature, which is very surprising. It's also a very loosely defined term, large scale is basically what's happening on the basin scale. Some people call it the Ekman pump. Some people go a little bit more general than that. So there's very little consistency as to what it actually comprises in terms of physical processes. And that's a recurrent theme in this talk, is that that's the very first step and very first conclusion that I came to and that we came to as part of our working group, is that the discrepancy of even in terminology is a big barrier to making progress in that part of the biological pump and its processes. So here you can see an estimate for that large-scale physical pump, whatever it stands for, being about a quarter, like 0.25 petagram of carbon per year. Doesn't tell me much, to be honest, because I don't have the general concept, but that seems to be weak compared to other things. And maybe that's why it hasn't got the attention and the robustness in the definition and stuff like that. There's also a nice paper by Laura Respondi that focused on the western part of the North Atlantic, trying to do a subtropical and strong jet and the subpolar region, and they get a rate for the Ekman pump that's about this. So the reason why I put that number is not so you actually pay attention to the number, but you can already identify the first hurdle here. Not the same units at all, and it's really hard to even put the two in context one way or another. And to me, that was a big challenge in trying to put this stuff together, is being able to compare numbers and see where the field stands at is very difficult in itself. Okay, and what about DOC? So we had a conversation, and we had quite a few meetings. I think it was monthly. We're trying to do this monthly, and for the last, 8 months, probably. And I think it took us a few months to realize that in our conversation of, carbon expert, we all really just meant POC. And then someone mentioned maybe we should look into DOC as well, because I heard it's important. And so we started scanning the literature for that as well, and Shooting has done a lot of work in trying to summarize and put everything together that we could find that was tackling the DOC. And this is paper by Hansel that provides a large-scale global DOC export for the pump. And so this is it. This is the summary table for that mixing process. We have two numbers from two studies that we can't even compare because they don't even cover the same pool of carbon. Okay, I'll let you think about that for a second. Okay, so now moving on to the second process that I mentioned, which was the seasonal mixed layer pump. And this is the poster child of physical mixing in the biological carbon pump. This is the thing that when you try to picture it, you understand easily what it is. And it's basically, the concept is, you have a mixed layer where you have a spring bloom with carbon growing, not a biologist, you can tell. And then eventually that thing, kind of the mixed layer shoals, and then that thing is advected along isopycnol. And then you have different scenarios. The following winter, the mixed layer just has the same depth and everything gets re-entrained. Whether or not that's exported is also a question that seems to remain open in terms of timescale that defines our export. But you can have a scenario where this patch of high POC is actually advected to a region where the following winter mixed layer is not as deep, and therefore that material is not re-entrained and can be considered to be exported. And so that's a very nice diagram from that paper. I also included a slightly modified version, because there's another scenario where you have the exact same thing with you produce POC in the mixed layer, and then the mixed layer shoals. And then over the entire, summer season, that particulate organic carbon actually sinks a little, right? Most of it has a gravitational sinking component to it. And so because of that, maybe they sink to a depth that's deeper than what the following winter mixed layer is. And then what do you do with that? Is that actually the mixed layer pump? Is that the gravitational pump? How do you separate those two things? And that's tricky. But the mixed layer pump is the one that makes me optimistic about how we can actually make things happen, right? We actually have a fairly well constrained number for that in terms of global estimate. So there's this estimate that comes from that paper here that not only has an estimate, but uncertainties on the estimate. Yay for them. This is good. And there's also this paper. So there's this paper by Dalmo et al. That did that very smart things where they took a climatology of mixed layer depth and they couple it with satellite estimates of POC at the surface and kind of make some assumptions and stuff like that. And then they estimate what the global distribution of the mixed layer pump is. Those kind of studies, this is, to me, so good and kind of a benchmark of how things should be done. You have a global number, you have uncertainties. The paper is actually quite well written in its terms that the methodology is quite well outlined, which is not always the case when you get those estimates. And also because you get the distribution now, actually, Onur was able to reach out to Giorgio and ask him for the data set, and we're able to look at the geographical differences, right, depending on the basins and stuff like that. A little bit about that in the other working groups as well, looking at different regions, and I'll talk about that in a second. But this is great. I think this is kind of the level that we should aim for when you provide the tool for the community to pick up on it and apply it in a different way. And this is all data-based. And one thing I wanted to mention about that is, it's data-based. The reason why he could do this is because of the Argo program. And I am so happy Harvey is here to talk about this, because the only reason we can have such a good number about it is because we know the mixed layer depth quite well. And that only took 5,000 floats. So we should do the same thing for other parameters. Deploy Argo floats. Those are good. This is my key message here. But this is great because, we all can also talk about the seasonality of it. We talk in terms of petagram of current per year, but unfortunately, this is a very, very strong seasonality in the mixed layer, right? This is in the mixed layer pumps. This is all when the mixed layer shows that most of the export is done early summer, as you can hear here by the MLP. And there's also strong regionality. So you can see here on the global distribution from the almost paper that there's definitely hotspots where the mixed layer pump is active, and then some where it's really not. And so this is the summary of the global numbers that we got, and this is the number that I pulled from an obscure table in the supplementary information in the modeling paper. And this is what I mean by, those numbers are important. It is worth not hiding them deep into your methodology section. But they surprisingly agree. This is great. This difference is less than half a petagram of carbon per year, which is what we were talking about this morning in terms of viability. So this is encouraging, and then we can take this kind of studies and then break it down by region. We've had a lot of debates whether or not we like those regions, because coming from the physical standpoint, it's maybe a more dynamically based definition of region would be worth thinking about, but we also have to think about homogeneity across working group, and we can't just have one team drive everything. So this is something that is very much going to be a challenge when we try and merge our work from the different mixing groups together. But you can immediately see that there's regions where mixed layer pump matters a lot, and then there's regions where it doesn't as much. And so this is great. This is interesting, right? Because there's a lot of information in regional studies as well. So I don't go into those very much, but there's a lot of studies, and we talked about that. Someone that has a cruise, maybe 3 ships that have like a well-constrained box where they try to quantify this. But how representative is that number that you get for that region, for the whole world? And those kind of global studies is really the pivotal tool that we have that helps you, okay, well, I did mine in the North Pacific, whatever number I have is actually very much, it's supposed to be smaller compared to what the rest of the world would be. And so that puts a very valuable context onto smaller regional studies that we can start and unify because of that. Okay, what about DOC? Well, it turns out that paper in the same obscure table as an estimate. And, I say it's hidden in the supplementary information and all, but to their credit, it's still there. The number is actually reported, which is helpful. And that number is negative. Did not expect that. I know next to nothing about DOC. Maybe some people are less surprised than I am, but that's the number they report on. Okay, and so we get to the exciting part, the part that I actually, I was going to say care about. That might be other words. But the part that I've thought about the most, let's say, and that's the eddy transport pump. And so what do we mean by that? And I think we were talking about that with Philip earlier. I think one of the big barriers in people including this in their study and generalizing, quantifying that part of the pump is also the lack of visualization of what those processes are. It's really hard to imagine this kind of obscure three-dimensional process that happens at all type of, spatial scales and temporal scales. So it's harder to visualize. There's been a lot of work done recently trying to visualize that I think we started with the Oman paper in Science, maybe not started, but became quite on my radar anyway, thanks to that Science paper. And then that's basically the 3D conceptual view that we have of this. You have a large particle that sink out, that's the gravitational mixing group. I don't need to talk about that. But there's also slower sinking or non-sinking particles that are more susceptible to three-dimensional circulation in the ocean. And when you get tilting isopycnal, you can have vertical movements of water mass, right? You have a similar situation here. Instead of an eddy, you have it depicted along a front where you have a sharp front with a deep chlorophyll maximum, and then along that front you can have subduction happening and bringing material to the bottom. So we went from that 3D conceptual view and okay, let's try and model this, because that was also all motivated by the fact that models were starting to get smaller and smaller and capturing smaller scales with those vertical movements being better resolved. And this is a paper, it's called the wine glass. I forgot what it's called. It's something about wine glass, because they basically look at, an eddy and the vertical velocity. You can see the flow field here along the isopycnals in gray. And then those red lines are basically what happens to particles that are trapped into that eddy as they sink with different sinking speeds. And so the fast sinking one are barely deformed in terms of they sink straight down. That's great. The slow or almost non-sinking particles are actually advected and kind of funneled, and then that looks like a wine glass. And so that's what they refer to. And then eventually we moved on from that two-dimensional model view, and we started observing those things. We actually developed the instrumentation and the capabilities of capturing those things from Argo floats. Surprise, surprise. A lot of people have done work about that, detecting subsurface anomalies and being a trace of what subduction. So here you're looking at a 2D transect that we capture as part of a program in the Mediterranean Sea across a sharp front, exactly like the one depicted in that conceptual view. And then you can see the mixed layer depth in the thick black line. And then you can see oxygen, chlorophyll, and backscatter, and there's clearly a tongue of material being subducted down. Okay. I remember when we saw that data for the first time on the ship, and I remember cheering, because there isn't that much observational evidence of, anyway, at the time anyway, starting to develop a little bit more, and that's great. Now we can observe them, and there's so much potential in this data set. Okay, so how do we quantify the eddy transport mixing pump? I have no idea what I'm doing for time, but there's different ways of doing it. And so what we're trying to quantify really is the covariance between the vertical velocity and whatever concentration of what you're trying to trace. In our case, carbon. So you can see it, vertical velocity, W, and the carbon. That's great, but if you want to do it from observations, that's something that's really hard to do. And that's actually one of the challenges that I'll talk about a little bit later, is measuring the W is actually really, really tricky, right? And so if you want to do this work from observation, you have to start doing some parameterization and building some assumptions, which Mara has done in a preprint that's available. That's very, very nice work in how she can actually parameterize that flux and produce a global map of that. And that is I can't even find the adjective. This is great. This tells us so much. First of all, it tells us about, places where it matters and where it doesn't, which is also the information that the Almo paper had for the mixed layer pump, which is great because now we can try and see if those gas work together or against each other. But also, I think the most important result to my eye in that figure is it's contextualized with, sinking fluxes estimated from previous publication, and the frontal subduction fluxes tend to exceed those sinking fluxes. So the gravitational pump is something we have been talked about for decades and decades. And again, I believe it's because it's easy to mentally picture, right? It's very intuitive. You have things that just rain down, and it's probably easier to quantify as well. But this eddy subduction pump that has, smaller community you're looking at, I guess, it matters. It matters a lot, and sometimes it matters most, which is, I think, a key message here. Anyway, so you can do it from observation. You can do it from model. It's a lot easier because you actually have W, so you can just use that product and compute it. This is a global map from a paper by Levy et al. And then you can see the same thing that I was highlighting earlier, completely different units, completely different carbon pool, different sign. Positive is actually the opposite. To me, that's just a big barrier. And as a community, I think it's time to, come up with guidelines of there's no right way or wrong way of doing it, but we should agree on which way, I think. Okay, so this is a little exercise that we did in trying to come up with what the vertical profiles would look like for POC fluxes. And so based on the same approach that I detailed before in the Freilich et al. Preprint, you can take the mode one of what the vertical velocity would look like in the ocean, and then you take a profile of POC that you can get from cargo floats, and you can multiply the two of them and then see. And then this is actually something that has been mentioned in the literature quite a bit. Like you see, it peaks around the 100 meters horizon that we tend to use for export. Another soapbox moment for me. Why the 100 meters? I don't know. And then it quickly decreases. And that's actually something that was highlighted in a study recently by Stuckel et al., where they found the same thing. The flux is very, very high at 100 meters, but it quickly attenuates. What does that mean for actually sequestrating carbon? I don't have the answer to that, but I think that's a valid question to ask. So there's also other parameterization that were done to try and capture what the impact of mixed layer eddies were. So eddies are confined to the upper part of the ocean exclusively, and this is the paper by Ullman et al., which no, it's right here. That kind of used some of in-situ data to verify that parameterization and trying to extrapolate it to the entire hemisphere in terms of for the time of the spring bloom and how much eddy-driven subduction you can expect. And you can see that the North Atlantic is very active, as well as the Southern Ocean. And if you go back, that seems to be quite aligned with this kind of work as well. Okay, so this is great. We can start, maybe the numbers are not very clear to cross-reference and takes a little bit of work. It's not impossible, it just needs to be done. Someone needs to put the work and effort in, which is what that working group is about. But at least on the geographical distribution of it, we learned quite a bit. Okay, yeah, okay, that works. And so we got an estimate for the eddy subduction pump for that white paper that really tackled all of the different pumps, and that's great. It comes with uncertainties that covers two different signs, by the way. So, and that's actually my last point, I think, is that when you look at the estimate, so from that work by Freilich et al., we can try and actually get a number here, and we're in the process of doing that, but the numbers we have so far varies in sign. We're not even sure which way it goes. And one of the reasons for that is because as you start going to smaller and smaller scales, those, and what we call sub-mesoscale, which would be, 1 to 10 kilometers maybe, and smaller than that, you enhance vertical exchanges. This is a model field from a study we published a few years ago, where the sub-mesoscale, the fine scale activity is really active, and you can see very hot spot of very strong vertical velocities. And those are very localized and can they have the potential, but they're also confined to the mixed layer, and they have the potential of moving material quite fast, but not necessarily quite deep. And because of that, and because everything that goes down must go up, there's actually a lot of work being put in, look, what is the net effect? Are we actually subducting? Are we abducting? And the results are not quite conclusive just yet. And so what that paper by Responded et al. Found is that if you actually start averaging all of those fluxes up and down, you actually end up close to zero, which have a very small contribution to that. That eddy subduction pump is actually a small contribution. And that kind of is aligned with those global numbers that we see that actually vary signs within our uncertainties, because we're not sure quite yet. And that might be the reason. The reason might be because we can't capture those scales just yet. As you go finer and finer in resolution, you create more of that asymmetry in downwelling versus upwelling. So downwelling velocities tend to be stronger but more localized, and upwelling are wider areas but weaker. And that asymmetry becomes more and more prominent as you go as you resolve smaller scales. And that's actually a graph that is very instructive. Is, this is our capabilities in terms of modeling, and then what's projected in terms of like the processes we might be able to capture in models. And if you start talking sub-mesoscale, 2035. So there we go. I propose that we just sit for 10 years and then wait and then look at it then. I am running out of time, but we do have thought a lot about how that will change with time. And so one of the good things that came out of that exercise is that it really forced us to think about what the underlying metrics are. What do we care about? For example, the mixed layer pump is easy. You care about mixed layer, you care about POC concentration, just to make it simple. So how are those going to change with time? And we kind of know, people have thought about, individual metrics, how they're going to change through time. And so for the mesoscale eddy transport, there's quite a few studies now that came out about how the kinetic energy of the ocean is changing, whether or not it's increasing, decreasing, but at the very least, the distribution is changing, and that because we've seen that the different pumps have very localized, they're stronger in some places than others, that might actually matter. And then it's the same thing for the net primary production, right? It's forecasted to actually decrease, so you're playing with the POC concentration now and how that's going to change. And even if it doesn't decrease or increase, even if we're not sure about that, it's going to be redistributed at the very least. And so those are things that we can start thinking about. A lot of people have, and it's just really a matter of cross-referencing all that information together to have the complete story about it. Okay, so what can we do? For the biogeochemical part of that, we need more data. I think I'm like the 10th person to say that in the last 2 days. We just need to better constrain it in terms of data. And that means doing regional studies, but when you do, try to contextualize it into a global framework so you can make it easier to compare in between studies. And that also includes maybe look at DOC. I don't even know how you measure DOC. I have no idea. I had to Google it earlier and I couldn't even understand it with a little Google blob. So I'm not saying it's easy, but I'm saying I'm sure someone in the room knows how to sample DOC. And it's worth looking into because there's a lot of uncertainty associated with that. In terms of physics, measuring vertical velocity is something that I think is getting traction in our community, and trying to actually quantify that is very difficult, but very important for many reasons. And in terms of biological aspect, now there's also like, you're bringing different communities to different depths, you're advecting them, what does it mean for the actual organisms and the biological signature of that water, and what does it mean for the amount of carbon that you're actually moving around? All of those are questions that I think we should focus on a little bit. Okay, I'm going to finish with that thought, which is something that Andrew put forward in a very valid point, and that is the risk of double counting. And I mentioned it quickly about the mixed layer pump. What is gravitational pump? What is mixed layer pump? Dividing and conquering is great. That's the only way in my head I can function, is breaking it down into smaller parts and then looking at those. The problem is that all of those are interdependent. Doesn't mean it's the wrong way of doing it. It just means that we also have to spend some time understanding of how those are connected and whether or not there's a risk of overestimating or underestimating depending on the processes you look at. This is an example, and you might have seen this on the poster. yesterday, but when you look at the eddy subduction pump and the mixed layer pump, there's many opportunities to be double counting, depending on what the scenario is. And so that's something that I think we should be really careful about. Okay, so Adrian said we need to plant our flag with what the estimates are, and this is what our flag looks like for now. And you can see there's still a lot of holes in there, but hopefully we'll get to work on it and improve it. So if you know of tools, if you know of studies, of data sets that are maybe low-hanging fruits, bring them forward. This is what the working group is about, right? It's trying to, I don't know the whole literature, and it's really relying on the breadth of knowledge and expertise that JETZON has. So I think that's it.
Time for a few questions.
Oh yeah, I just want to add some credit to Chloe for that. That quote from yesterday was amazing. It's so all over the place that oranges are not even in there. I don't know if you noticed. I was baffled. That was great.
Cool. Great. Thanks. That's a really good talk. So it occurred to me about halfway through. So for DOC, we have the common thing we think about DOC. There's a component which is almost uniform in concentration across the water column, about 40 micromoles per kilogram, and it's got average bulk radiocarbon age of about 4,000, 6,000 years. So it's basically just spinning around the like overturning cycles. So when you're thinking about export in terms of DOC, in terms of this pump, you're effectively entraining that kind of background DOC, because you're basically saying the standing stock of DOC is being mixed down from the surface into the interior. That's quite different to, I guess, the concept that we have in biochemistry, where the export might be the production flux of DOC in the surface, with a fraction of that getting into the interior. So I thought that was there's a kind of not quite double accounting, but a different way of thinking about what export means in terms of DOC for that respect.
Yeah, I mean, I think this is a recurring theme, right? As I don't think we all have conceptualized even what we mean by terminology.
Yeah.
Part of DOC means different things. Just in this room, I'm sure.
I think, yeah, it's part of the DOC that kind of it goes past that typical thing of thinking about surface export into the deep and then coming back up. It kind of going round and round and round. So yes, I think that's a thing to think about.
Laurent, behind you.
Laurent Memory from Brest. I'd like to know, when we are dealing with those export fluxes, it's really export fluxes in the subsurface, let's say below 200 meters, something like that. But the point is that it is linked to small time scales, because if the export is not transported downward, deeper, I'm not sure it is very important for carbon storage. So I like to know what is the fate of this exported carbon at very shallow depth. What happens after? I think it's one of the main points in terms of carbon storage.
So I started working on this question in 2017, I think, and I think I've been having this conversation since 2017. As part of that project, we had a lot of conversation about what it means to be exported. How long do you have to stay down there to be considered exported? And that's exactly the point. I think that's why this pump is harder to constrain. It's because the time scales are much shorter, and so things get re-entrained. But also, when you start combining that eddy pump with the gravitational pump, and this is kind of the point of one of the studies that I was mentioning about that we wrote, was when they start working in partnership, then it does, it pushes things down to the base of the mixed layer much more effectively, and this things, and then the gravitational pump can take over. And so it's hard to know what the subduction pump alone does to that carbon storage, because it is not alone. It works in coordination with other pumps that you require. If you just look at the AD subduction pump, that paper by responding et al. Shows it is most of the things is going to come back up in a time scale that, you know, for carbon sequestration is irrelevant. It comes down, it goes back up, and maybe we don't need to count it. But when you start having this interplay between pumps, I think is when it actually can become interesting. And so that's the study we did is actually we tried to couple that gravitational thinking with that AD subduction pump, and then see if you make the two work together, what does it mean to the flux? And we showed that it enhances the flux, the export flux quite a bit. And so that's why I think the subduction pump matters. That answers your question. I meant to preface saying that I wasn't going to answer questions, but I forgot.
Take this last question and then move on to the lightning talks.
Isn't, part of the answer to that question is what is the science question you're asking? And then like sort of sequestration is a different question than shallow mixing that might affect short-term budgets, seasonal changes. So what I would just say is you've got to put a bill up there on depth, because these things, unless you have a depth next to them, they really are meaningless, to me anyway, for the questions I'm asking. And then if you think of depth alone for the gravitational flux, even that's sometimes the wrong boundary, right? If you're picking a depth that's well above or well below where light runs out, you get a very different view of that biological carbon pump, what we started with today in the other session. So I think we really have to be careful with the vertical dimensions, and depth might not be the right one, but if we don't put on these, we just can't. It's lemons, apples, raspberries, and I don't know, Raspberry Pi computers or something.
And cows. It's like, your point is exactly the point that when you say what are the science questions, I don't even know if we know what the science questions are, and I think that's why the disparity comes from, right? Is that we don't even really have that common sense question, and that's why you have 100-meter horizon, euphotic depth horizon, 1,000 meters horizon, and that,
On to the lightning talks.
I think there was one last question, but we can talk.